Hello everyone, welcome to my channel. In this video, I'm going to talk about multi-version concurrency control in in-memory OLTP. We will explore the row structure that enables concurrency, and we'll take a detailed look at how select DML statements are run against these rows. You'll be able to deeply understand how in-memory OLTP provides concurrency without using any logs and latches. Let's get started. First of all, let's discuss about data row structures in in-memory OLTP tables. We call in-memory OLTP as hackathon. So allow me to call in-memory OLTP as hackathon from this point. Suppose we have following data saved in hackathon table. I have created hackathon database and this table by using following T-SQL queries. Every hackathon table should be created with index. Here I'm creating the table with hash index with bucket count equal to 26, and the index is on middle name column here. Please refer to my next video on hash index for further explanation on how hash index works. Okay, so I'm not going to talk about in detail about hash index here. So as you can see, I'm specifying also memory optimized equal to on, since this is hackathon table, and I'm setting durability equal to schema and data, since I need data of this table to be durable in the case of SQL Server restart. You can also set this value to only schema if you are okay to lose data in the case of SQL Server restart. I have inserted this table data with one batch insert query. Okay, and now let's have a look at how each row of this table is saved in memory. In memory OLTP tables, row structure is different from the on-disk rows. All hackathon rows are saved in this form, as you can see. There is a header and payload part. Header part starts with begin TS. This is the insert timestamp. This is the transaction commit time which inserted this row. We call this time, but this is just actually a counter. Then comes NTS. This is a delete timestamp. This is a transaction commit time, or we can call it counter, which deleted this row. Then comes statement ID of the statement, which inserted this row. Then IDX, link count, number of indexes that reference this row. In our case, we have one hash index, so this should be equal to 1. Then comes padding. Then after padding, there is a pointer. This is a pointer to the next row in each index. We can create up to 8 indexes per table in hackathon, so we can have up to 8 pointers here. Now, since we have only one index, we have one pointer. Last one is data payload. This is where actual data and index is saved. This structure of the row helps to provide concurrency in hackathon tables. So every time you insert a row to a hackathon table, rows are saved in this form in memory. So if we look at our actual data in this format, we will have this outcome. We have RAM, we have index, and we have rows saved in different parts of the memory. As you can see, I used one batch statement to insert data rows, so commit time is the same for all the rows. I did not delete these rows yet, therefore there is no timestamp for and TS for any rows. Then statement ID, as you can see, is the same for all the rows since only one batch statement is used. As you can see also, there are links to the next row here. Finally, we have data here. I did not include all the columns, only middle name column here, since we created index on this column. Now let's see how select query works in this case. Suppose we are running following query: select from OLTP table where middle name equal to A, right? Now, firstly, the ID of this transaction is recorded. Let's say it is 3. Next, SQL Server goes to index check, finds A in our index table and corresponding first row. Then begin TS and end TS is checked and they are compared against transaction ID. If transaction ID is bigger than begin_ts and lower than end_ts, this row is returned to the client. If not, this row is just ignored, taken as this row is not available anymore. Here our transaction ID follows the equation bigger than 1 and lower than eternity equation, so we take this row. Then based on the next row feature here, we locate next row and the same procedure is repeated until the last row. Finally, we have 3 rows returned, so select query works in this way in hackathon tables. Let's see how delete statement works. Suppose we are running following delete statement and this statement is deleting this row. In the case of DML statements, along with transaction ID, which we already discussed, we have also global commit ID, which is managed by SQL Server. Transaction ID counter is recorded when our statement starts, and global commit ID counter is recorded when our transaction is committed. Okay, we can say this is like timestamps when transactions start and end. This commit ID is therefore always bigger than transaction ID. Suppose our transaction start at transaction ID timestamp 3. As usual, index is scanned and the corresponding row is found based on the where clause. But in this case, data row is not removed physically, but NTS here is changed to transaction ID timestamp. Okay, please pay attention to this part. Row is not physically deleted. After changing NTS, validation phase is started. Validation includes checking isolation level violations, checking dependencies, and hardening transaction log to disk. In other words, validation phase is necessary to keep integrity and durability of the data. After validation phase finishes, transaction ID is marked as committed, then commit timestamp is generated, and this transaction ID is changed to this global commit timestamp, which is 6 in our case. Now you know how delete statement is run in hackathon tables. Let's see how insert query works now. Insert query also follows nearly the same flow. Suppose you run some insert statement, transaction ID is recorded. After this, corresponding hash index is found. Suppose it is F in our case, and data row is added by linking to this index. Okay? As you can see, transaction ID is recorded in begin TS here. After validation phase, global commit timestamp counter is recorded and begin TS is changed to this timestamp. That's all. Finally, let's have a look at how update statement works. Nearly the same flow also works here. Suppose transaction ID is 8 and this update statement is changing this row. Update statement does not do any physical in-place upgrade. Instead, NTS is changed to transaction ID and a new row is created. Validation phase is run and global commit timestamp is set. Okay, the same flow. Okay, now we understand how select, insert, update, delete queries work in hackathon tables. Now let's see conflicting scenarios in SQL Server. For example, what happens if you run select query while update statement is in progress for the same row? Or what happens if update query is run while another delete query is in progress for the same row? How SQL Server resolves this kind of conflicting scenarios and ensures concurrency, data integrity. Here comes multi-version concurrency control mechanism of hackathon. MVCC is a concurrency control method used by hackathon to provide concurrent access to data in memory in the case of DML statements like update, delete, and insert, and it does not use any logs and latches. For usual on this table, SQL Server uses logs and latches to provide concurrency, right? I have courses for this, you can refer to them, how it works. But In the case of hackathon, concurrency is provided without any locks and latches. How? Let's see how it works. Suppose delete transaction starts with transaction ID 100. This transaction is going to delete this row. NTS has been changed to 100, as we know, right? So now we are in the validation phase. While this delete statement is in progress in validation phase, another select transaction with transaction ID 102 starts, and this transaction is trying to read the same row. It scans the index, locates the corresponding row by using index. As discussed before, then it checks begin TS and NTS. It finds that there is NTS value and it is lower than 102. Then it checks whether this transaction is complete or not. It finds out that this transaction is not complete and in validation phase. As a result, it returns this row. It says as if like, this is not complete yet. Let's take it, right? In the meantime, delete statement completes registered global commit timestamp ID and changes the NTS to commit ID now. Afterwards, any select statement which is trying to read the same row ignores this row because there is commit timestamp now. This is how concurrent control MVCC works. This is how read-write conflict is resolved without any lock and latch. Now, let's see what happens if two DML queries are run at the same time. First, delete starts with transaction ID timestamp 100. It locates the row to delete and changes the NTS to 100. In the meantime, another update statement starts and it's trying to update the same row. It locates the row and afterwards find out that NTS value has been already registered here, right? It means another transaction is already doing some kind of change. Then it optimistically assumes that that previous transaction will eventually succeed. Therefore, it aborts. In the meantime, the first previous query commits after validation and registered NTS accordingly. So, to summarize, if two DML statements are run and conflict arises between them, the second one aborts. Okay? This is how MVCC works, without any lock and latch. So to summarize, in this video we learned about how row structure in hackathon table, query execution flow, and MVCC, right? In the next video, I'm going to talk about indexes in detail. Please stay tuned and do not forget to subscribe. Thank you.